Aloha class, here we go. Let's get into section 2.1 part 2. And we're going to deal with 3, maybe 4 types of topics when we're dealing with this. First one, determining limits using algebraic properties of limits. And what I'm going to start doing, because I know you guys will probably get sick of it, is hit pause right now to look at that understanding, objective, and knowledge. Okay, but I'll briefly just go over the topics here. Okay, topic 1.6, determining limits using algebraic manipulation. And the reason being for hitting pause and looking at these is some of these end up being kind of repetitive. Okay, topic 1.7, selecting procedures for determining limits. So depending on a result that you get, we're going to give you a lot of tools in that toolbox so you know how to deal with each type of situation when being represented. The fun thing about this section is we get to do some math. Okay, and you can show off your math skills. Okay, topic 1.8, determining limits using the squeeze theorem. We're going to actually introduce this one in class as we're going to do an old AP topic. It actually came up in the 2019 AP calculus test of how you use this theorem to help to determine some things when you can't necessarily do a problem algebraically using limits. Okay, so here we go. How to evaluate a limit. There's really 3 main ways that we evaluate a limit: graphically, numerically, or algebraically. Now, the part that I want you to fill in is what the heck do we do algebraically? There are some techniques that we're going to use that are going to help us to be able to. Ooh, I forgot to turn off that webcam. Okay, there's some techniques that we're going to use that we'll get into later of what we do algebraically. The first thing you need to know is sometimes graphically, sometimes looking at a table takes way too much time. So a lot of the times, well, every time, our very first step when evaluating a limit algebraically is direct sub. Plug a 3 into that bad boy. And if you notice, if I plug a 3 into this guy, I get 3 squared plus 2 equals 9 plus 2, which is 11. And since it's 11, I'm done. Believe it or not, if you graph this function and you look as we approach 3 from the left and to the right, the answer is going to be 11. Okay, it actually means the function value equals the limit value. Okay, if we look at b, okay, what happens when we look at b? Well, let's use that direct sub again. Okay, as x approaches, and that is not supposed to be a 0 right there. That is supposed to be a 3. So as the limit as we approach x approaches 3 of x cubed over x would be 3 cubed over 3, which would be equal to 27 over 3, which would be equal to 9. So same thing. Graph that bad boy as you approach 3 from the left-hand side, and from the right-hand side, you're going to get 9 as your answer. Okay, to save some time here, I'm going to fill these in for you. Go ahead and hit pause, and you can fill these in, okay? But let b and c be real numbers. Let n be a positive integer. Let f and g be functions with the following limits. Okay, so the limit as x approaches c of f of x is equal to L. The limit as x approaches c of g of x is equal to k. Remember, it's okay that they equal different y values, L and k, because we're dealing with 2 different functions here. But there's a lot of rules that we have to know about limits, and here are 6 of the very most important ones. Okay, and the first one, check. The limit of a constant is the constant. So let's say the limit as x approaches c of 5, it's equal to 5. Why? Because it's actually just being represented by a graph of a horizontal line. Okay, the limit as x approaches c of f of x plus or minus g of x is equal to L plus or minus k. And we say this is the limit of a sum or difference of 2 functions is the sum or difference of the limits. Next, the limit of a constant multiplied by a function is the constant multiplied by the limit of the function. Next, the limit of the identity function is c. The limit of a product of a function is the product of the limits. And last, the limit of a quotient of a function is simply the quotient of the limits, as long as the limit of what is in the denominator is not equal to 0. Go ahead and hit pause, write those out, and we will use those in some problems so you get a better understanding of what they mean and what they represent. to do that, we're going to go back here to this page. Okay, so how would we use those properties in problems like example 6? Okay, and we would use it like this. The limit as x approaches c of 5 times g of x. Okay, and we're allowed to use those two pieces of information right there. But to use those two pieces of information, I've got to show that I have it in the problem. For example, this one here, there's no 5. There's no 5 in this g of x function here. So what I need to do is, since 5 is a constant, I can bring that constant out in front. And yes, you do have to show this work. It's a tool that we have in our toolbox now that now I can use substitution, so I get an answer of 15. Okay, our next one is the example of a limit of a sum is the sum of the two limits. Do I need to break it up? For sure you do, because once again, we are showing that we are using direct sub. If you remember your fun geometry days, these are kind of like proofs. Let's go ahead and use direct sub there. Let's go ahead and use direct sub there, and I get an answer of 5. C, the limit of a product is the product of the two limits. Do you have to show this? For sure, because we're using substitution. And when you're using substitution, you have to show that you have it in your problem. I definitely was given that bad boy. It's equal to 2. It's right up there. I was definitely given that bad boy. It's equal to 3. It's right up there. 2 times 3 is 6. Check out those math skills. All right, and our last one. The limit of a quotient is the, whoops, I should have did this first, is the quotient of the limits. Remember, can do this as long as the denominator's limit does not equal 0, and guess what? It does not, using those givens at the beginning. Okay? Okay, class, what is the very first step when dealing with any limits? Direct sub, right? Let's plug in a 1 right there. What do we get? Negative 1 squared plus 1 equals negative 1 plus 1, 0. Done. I hope the quiz is this easy. Next one, let's plug in that 3. Square root of 3 plus 1 over 3 minus 4 equals square root of 4, which is 2, over negative 1, which is negative 2. Bang, I'm going to ace this first quiz. Now, there should be parentheses there. Okay, shame on me for not putting them on this document. Okay, plug a 0 into that bad boy. What do I get? Oh, 0 and plus 0 equals 0. And the last one, please put parentheses right there. It has to be there. This one's a little bit tough, messes some students up. I got 2 variables here, but guess what? It's just a limit as h approaches 0, very first step, right, class? Direct sub, plug in that 0, and I get 3x squared. That's my answer. Seems crazy, but it's okay if it's got that x in it like that. That is the answer. That's what the limit is as h approaches 0. It's 3x squared. All right, so here we go. I know it says day 2 there. It just means we're going to get crazy into day 2 here now. And it's other strategies for finding limits, right? You're probably like, man, is the first AP calculus going to be that simple? Just direct sub? Direct sub, yes, it's that simple, unless, bang, 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 you get 0 over 0, which would mean there's a hole or a removable discontinuity, which we call this an indeterminate form, which you better do something else when you get that result of 0 over 0. And I've got 3 techniques laid out here for you of things we do algebraically to still help us to find a limit. Now remember, one thing you could always do is graph. But sometimes, hey, if you got to do a graph without the use of a calculator, that can be pretty tough to do. Now, as you go through all these things, there's going to say a lot of note cards. I highly encourage you to do these note cards. Anything important you put down on these note cards, and it's always very, very helpful to look back. Do you have to do that? No, you don't. But I find it very, very helpful. Oh, here we go. Example 1. The limit as x approaches negative 1 of 2x squared minus x minus 3 all over x plus 1. My first step, everybody at home, is to direct sub that bad boy. Let's go ahead and plug 1 in. Bang, bang, choo-choo train. I'm pretty fast. 0 over 0. That means there's a removable discontinuity or a hole. So what does that mean, class? That means I better do something else. Well, I don't know about you, but that numerator definitely looks factorable. So let's go ahead and factor that guy. If I were you, I would maybe hit pause. Some of us, we struggle with factoring. If you do struggle, please make sure you come in for some help, and we'll do a whole bunch of factoring problems together. Okay, but if I factor the numerator, I get 2x minus 3 times the quantity x plus 1. And if you notice, something cool happens right now. Okay, for 1, if I plug a -1 in here, I still get 0 over 0. But check this bad boy out. Bang, bang, choo-choo train. Those guys cross out. Now, if those guys cross out, guess what they're doing? They're actually getting rid of our 0 over 0. And now, after I go ahead and factor and cancel some things out, the question is, we go back to step 1, which is direct sub. And if I direct sub into this bad boy, I get 2 times -1 minus 3, which is -5. So the limit as x approaches -1 from the left or from the right is equal to -5. Don't believe me? Go ahead and graph that bad boy. All right, example 2. Everybody at home, what is our first step? Direct sub. You direct sub that bad boy. Remember, you never write that word limit when you direct sub. I get 0 over 0. What does that mean? Do something else. Well, that definitely does. I don't know about you. Does not look factorable, but it does have this word. I gave you a technique earlier that used this word rationalize, right? And whenever we see a square root, you should think rationalize. Now, normally in pre-calc algebra 2, we rationalize denominators. In AP Calc, what happens sometimes, often, is we rationalize numerators. So let's go ahead and rationalize that numerator. Once again, why am I doing this? Because I'm getting 0 over 0. And I don't know about you, but I wouldn't want to graph that bad boy by hand. So let's go ahead and try something algebraically, which would be the limit as x approaches 3 of the square root of x plus 1 minus 2 all over x minus 3. Now, what does it mean to rationalize? Well, we multiply the numerator and the denominator by the conjugate. This time, it's multiplying by the conjugate of what is in the numerator, which is the square root of x plus 1 plus 2. Now, why do we do conjugates? Well, you're going to darn well find out. One thing is in the numerator, our math gets helped out a little bit. How does our math get helped out? Well, whenever you're doing conjugates, you can skip the outside and the inside of FOIL. And all you have to do is multiply the 2 first dudes, which gives us x plus 1, with the 2 last dudes. Why? Because the outside and inside will always cancel out. Now, an important notation is x minus 3 is a quantity. You better put parentheses in that when you're combining this denominator. Okay. Now, the interesting thing, you're saying, Mr. Tanaka, that doesn't help me out because if I plug a 3 in right now, I get 0 over 0. And you know what I'm going to say is I'm going to say you're a smart cookie. It gives me 0 over 0. But if you notice, I haven't really crossed anything out yet. So let's simplify that numerator, right? I can simplify that numerator. Oh, shame on me. You better write limit. The only time I don't have to write limit is when I use direct substitution. So it'd be x minus 3 in the numerator, and in the bottom I get x minus 3 square root of x plus 1 plus 2. And if you notice, there's an x minus 3 in the numerator and the denominator. Bang, bang, choo-choo train. Gets rid of my 0 over 0. I'm still going to write this word limit. Why? Because I haven't necessarily direct sub yet. Sorry about this. Let's just get away. Okay. And on the bottom, I get the square root of x plus 1 plus 2. Now let's direct sub that bad boy. Do I have to write limit? No, you don't. And you get 1 over. We're all smart. I'm going to do this fast. What would that be? 1/4. So the limit as x approaches 3 of our function, the square root of x plus 1 minus 2 all over x minus 3 equals 1/4. So even though there's a removable discontinuity or a hole right there, the function value goes to 1/4. Example 3, the limit as h approaches 0 of what we call a complex fraction. I am going to rewrite this. All right, sorry, class. We had to rewrite that and able to solve it. That's a complex fraction. Shame on me. First step, right? Direct sub. I get 0 over 0, which means do something else. Can't factor that guy. Definitely not a conjugate problem, but you could do some algebra stuff. Okay, right? I have a complex fraction, which is 3 many fractions, right? That's really x over 1. Okay, and so what I want to do is use my concept of an LCD. My LCD of my 3 many fractions is 4 times the quantity x plus 4. So what I'm going to do is I'm going to multiply everything in the top by that and everything in the bottom by that. And if I go ahead and do that, you're going to notice some things beautifully cancel out. Now, I'll show a little bit of this work. If I lose you a little bit, this is where you can hit pause, make sure it all makes sense. But you come in tomorrow, and you make sure you ask for help. Okay, but let's go ahead and distribute this to that guy. If you distribute, you notice the x plus 4s are going to cancel out. And when you do that, what is left is just a 1 times a 4 or a 4. Now, if I distribute this to this one, the 4s cancel out, and you're going to subtract the quantity, x plus 4, and that's all over 4x, x plus 4. Now, we don't ever like to simplify the bottom, okay? Because if you notice, some cool things are going to happen if I don't simplify the bottom. Now, plug in a 0, you get 0 over 0. But there is some simplifying you can do on the top. The 4s actually cancel out when you distribute the negative correctly. Okay, and you're going to end up with negative x over 4x times the quantity x plus 4. Okay, plug in a 0, 0 over 0, but bang, bang, choo-choo train, those x's cancel out. And when those x's cancel out, I get the result of negative 1 over 4 times the quantity x plus 4. Now you plug in a 0 and you get the answer of negative 1 over 16. Now, if you notice with that answer, the limit as x approaches 0 is going to approach that height. Okay, even though when I plug in a 0, the function value gives me 0 over 0. Now what we get to do is one of my favorite problems in AP Calc. Why? Because it gives me a cheat. Okay, and that's the limit as x approaches 0 of sine x over x. Now, to able to introduce this guy, we're going to look at the graph. Now, the graph of this guy goes from negative pi to pi, and as we approach 0 from the left-hand side, or we approach 0 from the right-hand side, it goes to the value of 1. And believe it or not, there's some big crazy proof that proves that for us, but you are actually allowed to always use this result. Because if I wrote out this original problem class, direct sum gives you 0 over 0. It means to do something else. And guess what? You can't factor that bad boy. Guess what? It's definitely not a conjugate. Guess what? There's no algebra you can do. So the only thing you can do right now is use this property. It's an equation or a result you're going to be able to use from now until the end of the year, which is if you have the limit as x approaches 0 of sine smiley face over smiley face, that answer is 1. And you're able to always use that result. It's a limit you always want to remember. Now it's like a proof. Okay, so if you're like me, you kind of miss your geometry days and you miss proofs. So these problems are like proofs. So let's go ahead and look at B right here. Okay, and the question is, when you're doing these problems, you want to say what represents the smiley face. Because when I look at this right here, that smiley face is stuck inside of that trig function. You can never bring values outside of a trig function. So if you look at here, it looks like the smiley face is 5x. So guess what that means? That means I have to have a 5x on the bottom. But shame on me. What's my first step, class? Plug in that 0. You get 0 over 0. Do something else, right? Can't factor, can't conjugate, can't do any algebra, but you can use this cheat. But it's got to be sine smiley face over smiley face. And the smiley face in this case is 5x. What I'm going to do first. Okay, that 4 is kind of messing stuff up. But that 4 is a constant. What can we do with constants when we are evaluating limits? We can always bring those constants out in front. Then I'm going to cheat a little bit. Okay, you're going to say, Mr. Tanaka, you're not allowed to cheat, and I'm going to say you're 100% right. But what I am going to do is I'm going to try a little bit of magic. I'm just going to put a 5 down there. Why? Because I want to. And if I have a 5 down there, guess what? You have sine smiley face over smiley face. But we have a rule in math. You can't change an actual problem, but you're allowed to change what it looks like. And guess what? If I put a 5 down here, I'm allowed to do that as long as I put a 5 up here. Why? Because 5 divided by 5 is what, class? It is 1. And if I multiply anything by 1, it's really the same thing. So what I'm doing right here is I'm not changing the actual problem. I'm just changing the way it looks. Now, if you look here, I put a 5x on the bottom. That's a constant. I put a 5 out here in front. Why? Because it is a constant. Okay, you cannot bring this 5 out. But guess what I could do with this 5 right here? I could bring it onto the outside. And then check this out. I get sine smiley face over smiley face. And so now you can use that awesome property from above, which is 5/4 times 1 is equal to 5/4. And now some of you guys are going to say, hey, I knew it was 5/4 from the very beginning. You kind of did. And on a multiple choice question, I would want you to use that. But hey, a lot of these things are not multiple choice. So you would have to show that much work. It's kind of like a proof, and you're using this very important property in your proof. Okay, let's look at the next one. First step, don't forget this time, Mr. Tanaka, shame on you. 0/0. Do something else. Can't factor, no conjugates, can't do any algebra. What? Actually, it does kind of look factorable. Okay, so let's look at that denominator there. Let's go ahead and factor that and see if it gets me anywhere. What's my smiley face in this one, class? It's an X, and I like to circle that. Kind of reminds me of the smiley face thing. Now, if you notice in the bottom, I can actually factor out an X. And when I factor out an X, bang, bang, choo-choo train, it kind of looks like I have a little smiley face situation going on. Well, but how the heck do I use this very important property that equals 1? You got to exactly get that within your problem. Well, believe it or not, I could just use this concept. It's a little bit hidden, but I could rewrite this and use properties of limits to go ahead and use that result right there. And it'd be the limit as x approaches 0 of sine x. I'm just going to organize over x times 1 over 5x plus 1. Isn't that the same thing? Right? That is the same thing. I'm just rewriting it differently. And then guess what? I can show off my calc knowledge, and the limit of a product is the product of two limits. Mr. Tanaka, do I have to show all that stuff? For sure. You better show it, because if you don't show it, you're just like skipping 8 million steps. And I'm allowed to use a super duper property. And the only way you can use this super duper property is you have to show you have it by yourself. I showed I had it by myself, so what the heck just happened there? That is equal to 1 times, now we're going to direct sub over here, right? And if you do all that stuff, you get an answer of 1 times 1, which is 1. I don't know about you, but that was an awful lot of fun to work with. Okay, now what comes up is called the sandwich theorem. And the sandwich theorem is this really cool thing right here, class. And it's actually really neat how it works out. What it is we're going to sandwich f in between two different functions, and it's going to tell us some interesting things about the results of it. Okay, and what it basically is that if the limit of g of x is equal to L, and the limit of h of x is equal to L, guess what it squeezes f to be? It squeezes f to be L as well. Now, to introduce this guy, we're actually going to look at it tomorrow in class, and it came up in the AP exam in 2019. So we're going to look at that next class. You're done for the day. Please bring your questions. Please rewind and look at anything else you need to get done. And then please make sure you're keeping up with your homework. Aloha.